Okay, welcome to our first lesson in trigonometry in the grade 11 curriculum. Um, it's really hard to jump into this stuff. I'm realizing as a teacher, I don't know if there's one really good way to start presenting this material. So this is the best I've come up with for now, and I played around with some things about these first two lessons, and so I'm not sure if this is the best way, but this is the best I can. This is the best I know how to do right now. And so it's funny because when you learn this stuff, after you learn it, you wonder how did you actually originally wrap your head around it. And I always go through that every year when I teach this, just exactly like how to wrap your head around it. So I hope I can give you the best way possible. Learning target 1 is graph a terminal arm given a point or a ratio, and find the angle made by the terminal arm. And so we're going to graph a line or a point on the XY axis, and we're going to find the angle made by that line. And the point, the line and the point are the same thing. So the point is just is a point from 0, 0, and there's a line connecting 0, 0 and that point. And so what we're actually going to start to do is develop like a way to evaluate and solve for angles that are bigger than 90 degrees. And so this is how we're going to start to do it. So we ask the question, and you can see that we get angles that are bigger than 90 degrees, bigger than 180 degrees right away. And so that's going to be the point. How are the angles similar? So you have 45, 405, 765, negative 315, and then 30, 150, 210, and 330. So just like you to think about that for a second. The first one is, the question is like, if you turned 45 degrees, if you turned 405 degrees, you would end up in the exact same position. And that position, what we're going to call that is the terminal arm. And so pretend like you're standing and you turn 45 degrees. Well, if you turn another 360 degrees, that's a total of 405. If you turn another 360, that's 765. And if you actually turn from the 45 back the other way, like down 315, you end up in the same position. And so no matter what you are, the angles will get you in the same position. Okay? Sorry, not from the 45, but from your original position. If you turned back 315, that would be the same as if you turned 45 the other way. The second one, they all have something to do with 30 degrees. And so the first two, like if you remember your grade 9 rules about supplementary angles, 30 and 150 are supplementary to each other. And then actually 210 and 330 are similar to each other as well. Each of them somehow relate to 30 degrees. In fact, they are all 30 degrees from 180 or 360 or 0. And so that's actually going to matter in the end. And so between today and tomorrow, we're going to warm up with some of this stuff and just talk about some. I just want to plant some of these ideas in your head. How do they relate to 30? So you can see there's the 30 degree angle. That's the 150 degree angle. I'd ask you how can you get 210? So if you see the 210 here, and then how do you get 330? This is actually the 330 degree angle. So they're all in there, and they're actually all going to be related. What I'd ask you to do, and we're going to do this tomorrow too, is take the sine of 30, the sine of 150, the sine of 210, and the sine of 330, and see what you get. Okay, so here's what we're looking at. Given a point on the terminal arm of an angle in a circle with radius r. So if you've got a circle here, the radius is r, so it's a fixed radius, and you've got a point on that graph that looks like that. And this guy here is actually what we call the terminal arm. This here, and the angle. We call the angle theta, and you might know this already. It's just the Greek letter theta. It's used for angles. So this arm here is what we call the terminal arm. It's just the point that connects the origin to the radius of the circle. With that, we can actually draw a 90-degree triangle and put the 90-degree angle, but this is a 90-degree triangle. We can start looking at that angle in an interesting way. If that's x comma y, this length is x, that length is y. And the other length, the radius, is r. And Pythagorean theorem is going to hold true: x squared plus y squared equals r squared. So this is a 90-degree triangle. Okay. So now, if we recall SOHCAHTOA, we actually have the primary formulas for the primary trig ratios. The primary trig ratios are what we refer to as sine, cos, and tan. But if we go from that angle and do opposite over hypotenuse, we get y over r. Y over r is opposite over hypotenuse. Similarly with cos, if we do adjacent over hypotenuse, we get x over r, and tan we get y over x. Okay. And then new this year, we actually talk about what's called the reciprocal trig ratios, and all those are is just the other way around. Instead of opposite over hypotenuse, we do hypotenuse over opposite. We refer to this one as cosecant. There's the secant, which is the reciprocal of cos, and that's all they are really, is the reciprocal. And cotangent, which is the reciprocal of tan. Okay, and that's all they are. It's just something we're introducing here. It's just something else we can use. It's just the reciprocal. And if you have if you have the adjacent on the top, that's actually cotangent. One helpful way to remember these, which ones go with which, are sine and S and C go together. The S's don't go together. It really would be nice if they did, but they don't. Sorry. Okay. So example here, we're gonna graph the point -3, 4, and so all we do is just plot that point. And we're gonna draw the terminal arm of the angle in standard position, and that angle is going to just be this guy here. It's always from the positive x-axis. So this is your initial position all the time, the positive x-axis, and then we're going to go around the circle this way, okay, if we want to find angles. And so the angle we're looking at is this guy here. Again, you might be a little bit lost about why we're doing this. It's really just to help uncover more knowledge about angles. Now we can actually, by using that point, we're going to actually get ways to solve for these angles. Okay. To find theta, we use SOHCAHTOA to first find beta, which is actually the related acute angle. And so the one I just showed you had the 90-degree triangle, but the problem is this guy's in this quadrant here. So if we're in this quadrant here, to actually find this angle, it's actually not that hard if we knew this angle here, because we know that these two angles add up to 180. Okay. So what we're going to do is we're looking at this triangle here, the one that just came up. The height of 4. The adjacent side is going to be -3. We can use the 3, but the -3 is actually going to come into play. And then the radius is 5. The radius just comes from Pythagorean theorem. Okay. You don't have to show this work if you understand a 3, 4, 5 triangle, but the radius is actually always positive. Okay. So now it asks the primary trig ratios first, and so what we do is to find the primary trig ratios are of the angle. So of the angle we just saw, we're going to try out these formulas that we saw on the last slide. Cos theta is x over r, so adjacent -3 over 5, and then tan theta is opposite over adjacent 4 over -3. The -3 on the bottom just doesn't look nice, so we put it on the side here. The reciprocals are just literally the reciprocals. So if you have a negative, it stays negative. Just take the reciprocal. Okay. Now, any of these three, these ones aren't on the calculator, but any of these three will actually give you the angle theta. But we actually prefer to find beta first. So we actually want to find the acute angle, because we know the calculator is going to give us an acute angle. And so what we're going to do is calculate the acute angle first. And to find beta, I'm going to stop clicking so that thing goes away. So to find beta, we take the sine inverse of 4/5. We could do the tan inverse of 4/3. We could do the cos inverse of 3/5. They're all going to give us 53 degrees. We recognize that's not the angle we want. The angle we want is from 180. 180 minus 53, which is 126. Okay? So you don't need to do all of this to actually get the angle, but we're just kind of uncovering this for the understanding to show that all 6 of these are easy to attain if you know where the point is. Okay. For the trig ratio sine theta equals -5/9, and it's part of the reason why we do all of these is because we're going to see a question like this where it could give you any of the trig ratios, and we got to find the angle. Okay. So we notice that it's a negative. Since it's actually a negative, the y value in sine theta is y over r. The y value must be negative. The radius can't be negative. And so what we have is a situation like this, where you've got a negative y value, which is under the x-axis, and the radius is 9. So we've got this little angle beta, which is between the axis, but the theta, which is actually what we're looking for, is the entire angle. So this beta is actually just going to help us find out this entire angle, and that entire angle will be 180 degrees plus beta. Okay, so we use SOHCAHTOA to figure that out. We already know the opposite side. The y value is -5, and the radius has to be 9. So really, all we're doing to find out this angle beta is taking opposite over hypotenuse. Notice how we really don't care about the negative sign. We just want to find what the opposite of the hypotenuse is. And in fact, actually, if you leave the negative sign in there, when you do the sine inverse, you're actually not going to get an acute angle, which is what we want. It'll give you different things, but the best strategy to do this is to first find the acute angle. And so our angle there is 213.75. Okay. Now notice how it said what might the angle be, and you might have asked, well, when you drew the y value as negative, why couldn't it be in the other quadrant? And it absolutely could be in the other quadrant. It could be -5 down this way and 9 this way. We still have beta, my little curve there. We still have beta, but the theta is actually different. It's a lot bigger. It's actually going to be 33.75, the exact same thing, because it's still the same opposite over hypotenuse. It's still the exact same triangle. It's just in a different spot. And the theta is going to be from 360. And you can check. What is the angle? If you took sine of 213.75, if you took sine of 326.25, I'd bet my money that I'm getting -0.556. By the way, when we do this in our calculator, we want to make sure our calculator is in degree mode. There's a radian mode and a gradient mode, which I'll explain another time. Okay, so some practice questions that you can do. Won't click. It's a little bit annoying. Page 299, number 2, 6, and 12.